Hello, students. So we have these eigenvectors and these eigenvalues, and well, in order to be an eigenvector, you have to have an eigenvalue, right? So every eigenvector is going to correspond to a single eigenvalue, but you might have an eigenvalue. Well, as a matter of fact, you generally have an eigenvalue for infinitely many vectors, right? Because you have a one-dimensional subspace there, right? All multiples of an eigenvector are an eigenvector. But sometimes you might not just have all multiples of a single eigenvector. You might have two different eigenvectors for the same eigenvalue, which are not multiples of each other. So we're going to need some definitions to deal with that. So let's try to come up with some. So what we're going to do is we're going to call it an eigenspace. So let T be an operator on V. Then the eigenspace associated to lambda is E lambda T, the set of all eigenvectors for eigenvalue lambda. Now I'm not putting a period there for a reason. What do you notice about the name? We're calling it an eigenspace. So space probably means it's going to be a subspace. But what don't we allow for eigenvectors? We don't allow 0 to be an eigenvector. Otherwise you get, everything. 0 works for every number, because t of 0 is always equal to 0. So, t of 0 is 2 times 0, and t of 0 is 3 times 0, right? So we would have this sort of paradoxical thing, like one eigenvector that has every single eigenvalue in the field. We don't want that. But we do want this to be a space. So if I actually toss in 0, I get a space. So what we're going to do is we're going to define the eigenspace for lambda to be all of the eigenvectors and also 0. Now you might say that's a little wordy. This sounds like a little iffy, like we're trying to make a fix. We're trying to, I don't know, put some spackle up over some hole in our definition and stuff to force this to be a space. But let's think about this for a moment. So what does it mean to be an eigenvector again? Well, you have T of V equals lambda V, right? That was our definition. And what we said is, okay, well, if this is true, then this is true. This operator sends V to where this sends V. I can move this over to the left, and I could even combine the transformations. So I get that. So what does this mean? It means V is in the null space of T minus lambda I. And as a matter of fact, anything in the null space of T minus lambda I is an eigenvector, because we can go in both directions, except for one thing, and that is 0. 0 we said we don't want to count as an eigenvector. But everything else in the null space here is going to be an eigenvector. So another way of defining the eigenspace, a completely, well, not completely different, kind of similar, I mean, similar ideas and all that. So another way of defining this is to just say this is the null space of T minus lambda I. And the benefit of writing it like this is we don't have to prove that this is a subspace, because the null space of any operator is always a subspace. So by tossing in 0 and allowing us to say, okay, I'm going to take the whole null space of T minus lambda I know it's a subspace. Okay. I mean, it's kind of also obvious too, even if we didn't have this, right? Because you know that if T of V equals lambda V and T of W equals lambda W, we know that T of V plus W is Well, by definition, because it's linear, let's not skip a step. I get this, which is lambda v plus lambda w, which is lambda v plus w, which shows that this is an eigenvector. And of course, for scalars, it's similar. T of alpha v, if you know that v is an eigenvector, is equal to, well, by the rules of linear transformations, this, which is alpha lambda v, which is lambda alpha v. All right, they're just scalars. We can commute them. So I write it like this. Oh, look. Lambda is an eigenvalue for the eigenvector alpha v. So we know that eigenvectors are closed under addition and scalar multiplication. Anyway, I mean, once we've tossed in 0, they are definitely closed, right? The problem might be that you'd subtract v from itself and get 0, or you'd have a 0 here, and then you'd get the 0 vector. So once we've taken that out of the mix, we get a subspace. Okay, so I think that's all I wanted to say about eigenspaces to start off. But basically what we're doing is we don't always get a one-dimensional subspace. We don't always get just multiples of a single vector. Sometimes we might get all the multiples of a single vector, and then something else as well, multiples of another vector, and then linear combinations of vectors. So we need a name for this. We call it eigenspaces. I guess one last thing to say is, with this definition, what if lambda is not an eigenvalue? Well, then there are no eigenvectors, right? That's how the definition of eigenvalue works. It's a scalar for which you have an eigenvector. So if you have no eigenvectors, what's in the eigenspace? Well, 0. Just this part here. So I'll say if lambda is not an eigenvector, then this still exists. It's just equal to the 0 vector. I guess I'll say that, the set of just the 0 vector. So still we can take the eigenspace, we just get the 0 vector. Okay, that's it for this video.